Hi there, my name is Ian Glish, and this is my presentation on predicting home prices using linear regression machine learning, examining key features influencing housing prices in Ames, Iowa. I was given two data sets on the topic of detailed information collected from 2006 to 2010 from the Ames, Iowa's Assessor's Office on information that was used to compute the assessed values of individual residential properties in the Ames, Iowa area. I was given two data sets related to the same topic, but they differed slightly to serve different purposes. One was used for training the machine learning model to learn patterns in the data, while the other was used for testing the model and to evaluate its performance on new data. There were 81 recorded features encompassing structural characteristics, interior and exterior attributes, location and dimension details, materials used, and quality and condition ratings. The purpose of this model is to identify the most influential features affecting home prices in Ames, Iowa. These insights were used to develop a multiple linear regression machine learning model for home sale price prediction. The target audience is home buyers and real estate companies and their agents, helping them estimate potential sale prices based on various property features. This model empowers the model's users with data-driven insights to make more informed decisions about the sale prices in the Ames, Iowa housing market. The training data set was 70% of the data, while the test data set was the remaining 30%. The test data set was missing originally the sales price column, since this was the target variable wanting to be predicted. I initially decided to use all discrete and continuous numeric columns as the basis of my model's features. So I focused on addressing the missing values by imputing them with the most appropriate central tendency value based on the data distribution of each column, with the median value being the most often used. Through feature engineering, I created 3 new columns, and later I used a method to convert 2 categorical columns into numeric data to be able to use them in my model. Extreme outliers were identified and adjusted to a reasonable maximum value specific to each column, but only done to the training data set to prevent data leakage to the test data set. I wanted to visualize some key features for the model, so I started by examining the correlation between a home's total livable area and its sale price. There is a strong positive correlation between this feature of total livable area and the target variable of sale price. I then analyzed the range of home sale prices per neighborhood. This gave me a sense of how strongly a neighborhood could serve as a predictor of a home sale price. Finally, I analyzed the range of home sale prices for each building type, which showed how strongly a building type could be a predictor of a home sale price. Before building my multiple linear regression model, I created a simple baseline model that predicts the mean value of a sale price from a training data set for every input of the test data set. This baseline sets a minimum performance benchmark for all future model iterations of mine. To evaluate my baseline model, I used a performance metric called the root mean squared error, or RMSE, which measures how far predictions differ from the actual values. The baseline model of an RMSE was $81,338.08. From looking at this adjacent visualization, the average home sale price is about $140,000. So this large RMSE shows a strong lack of accuracy. All of my model iterations will need a much lower RMSE to be a much better predictor of sale prices of homes. For my first iteration of my model, I used 33 columns of cleaned and imputed discrete and continuous numeric data, plus 3 feature-engineered columns for a total number of 36 features. To evaluate the model's performance, I used a performance metric called the R² score, which measures how well the model explains the data, with a value between 0 and 1, with a higher value indicating a better fit. Both the training and test data R² scores were high and close to each other, showing that the model performs consistently between the two. This model also got an RMSE of $33,504.49, which is much improved compared to our baseline model's RMSE. For my second model iteration, I began by converting the neighborhood categorical column into numeric data so it could be used as a feature. I analyzed how strongly each neighborhood correlated with the home sale price and selected the 3 highest and the 3 lowest correlating neighborhoods as features. This updated my model to have 42 features. I then recalculated the performance metrics and evaluated them. The R² scores slightly increased for both datas and slightly improved the RMSE to $32,190.01. These added features resulted in a modest improvement to the model. For the final model iteration, I converted the categorical column of building type to numeric data and included the remaining neighborhoods not used in the previous model iteration. This brings up the total to 65 features used. I recalculated the performance metrics and the results showed continuous improvement. The R² scores continued to positively increase for both training and test data, and the RMSE improved to $30,528.54. This final iteration showed improvement and a dramatic improvement from the baseline model. In summary, all of my model iterations outperformed the baseline model, showing that adding more and more features reduced prediction error for sale price. The first model iteration performed the strongest, and the following 2 iterations showed continuous improvement. The test R² scores were higher than the training R² scores, and both improved slightly with each iteration, as well as the RMSE. For next steps, I could continue improving this model by adding even more features through converting categorical columns to numeric data, while being mindful not to overfit the model. Thank you for attending my presentation. Please let me know if you have any questions.